Hey everyone, welcome back to my Calculus 1 series. In today's lesson, we're going to be talking about antiderivatives. So firstly, let's start off with the definition of what an antiderivative is. A function capital F is called the antiderivative of f, lowercase f, if the derivative of capital F is equal to f of x. And if f is an antiderivative of f, then we say that the most general antiderivative is capital F of x plus c. We include this c and it's just basically a constant. So if that doesn't make any sense to you yet, I'm going to try to kind of break it down. Basically an antiderivative, if we think about it, is if, let's say we have this original function called f of x, right? And then we take the derivative of it and we get to f prime of x. The antiderivative of this initial function is this function itself. So this would be, once we get into integration, you'll see, but basically it will be the integral of it. So the integral will kind of undo this differentiation, and essentially that's what this is saying, right? So the way it's worded here is that if we have this function big F of x, right, and then we take the derivative of it, we're going to be left with f of x. And this is through the derivative operator. However, the antiderivative of the function is this one right here. So again, it's the integral of this function right here. Now we're not going to get into integration yet, but it's important to know what the antiderivative is, and it's essentially the function that we had before we took the derivative of it. So this one right here, right? This is the function that we're talking about in the definition. However, this capital F is the function that we would have had if we didn't apply this derivative to the initial function. So we kind of want to find the initial function before we took the derivative of it. Now obviously there are a lot of antiderivatives, but I'm going to list out a table with a few of them. So here's a table kind of going over some of the antiderivatives. And here are a few starter cases. Basically, if we have a function, the antiderivative is just, well, the antiderivative of that function, and likewise for this case. However, for this one, we see it's kind of a little interesting. Before, what we used to do to figure out, let's say we started off with something like, we started off with the function x to the n, and we wanted to find the derivative of this function, right? We would drop the power, and then we would keep the base and then take 1 away from the power. This was our process to find the derivative. However, to find the antiderivative, we're kind of going to do the opposite now. So if we're starting off at x to the n, the antiderivative of this function would be us adding 1 to the power and then dividing by that power. So instead of dropping that power first and then subtracting, first we're going to do the opposite of things. So we're going to add 1 to the power and then we're going to divide by that power. Now this one might look a little more familiar. If you remember, the derivative of the ln function was equivalent to 1 over x. And now we can see exactly what's going on. I feel like this is the first example where you can kind of see what's happening. If we were to have this function, right, as I was saying, the antiderivative of this function right here is a function that it would have been before we were to take the derivative of it. So we have this function right here. This is the antiderivative of 1 over x because it is the function that we had before we took the derivative of it, right? Once we took the derivative of it, it turned into 1 over x. But before we applied the derivative operator to it, we had ln of x, and that is our antiderivative. Likewise with e to the x, the derivative of e to the x is just e to the x, so its antiderivative is e to the x. And likewise with all of these other different functions. Again, we can see it with this cosine one because let's say we start off with sine x, right? And the derivative of sine x, so the derivative of sine x is going to equal to cos x. So it would make sense that cos x's antiderivative is sine x because sine x was the initial function that we started with before we took the derivative of it. That's all this antiderivative is. It's essentially kind of going backwards from, you're basically trying to undo the derivative operator. So here's a quick example of how we can apply antiderivatives. Let's say we are asked to find f if f prime of x is this function right here. So again, we know that the antiderivative is the function that we would have had before we took the derivative of it. And that's exactly what this question is asking. It's saying find f if this is f prime of x. So it's kind of like us going back a step, like undoing this derivative operator. And again, we're just going to go ahead and apply some of the functions that we see from this table to what we have. So f would equal to the derivative of e to the x is e to the x itself. So that means that the initial function that we started off was e to the x. Because if we were to take the derivative of this, we would still end up with e to the x. So if we grab a look at this right here, this closely resembles what the inverse tan would actually, if we took the derivative of this, would actually be. So this would be, and that's essentially the same thing. So we know if we were to replace this with tan, and then we were to take the derivative of that, we would end up with this thing right here. So that means that f is equal to e to the x plus 20 plus, or sorry, not plus, times tan minus 1 of x. However, the one thing that we're forgetting is this constant. And the reason we need to include this constant is because let's say we started off with this f, right? Every constant that we can choose here, actually any constant, if we were to take the derivative of any constant, it would evaluate to a term of 0. So we don't quite know what this constant is, so we write this plus c. However, if the question were to specify something like, okay, f of 0 is equal to, let's say, minus 2, then we can go on to find this c. And let's actually take a look at how we would do that. So we would basically plug in 0 for everywhere, and then the output should be minus 2. So minus 2 is equal to e to the 0 plus 20 times tan minus 1 of 0 plus c. Now this right here is going to evaluate to 0, and this right here is going to evaluate to 1. So we're going to be left with minus 2 equals 1 plus c. And so c equals to minus 3. So now we don't have the most general antiderivative anymore. We have the antiderivative of this function because we were given this point right here, that f of 0 equals minus 2. So we can write that f is equal to e to the x plus 20 tan minus 1 of x minus 3. Now, if you're unsure, you can actually take the derivative of this, and you will see that you will end up with exactly this function. So that's all this question is asking us to do. It's basically asking us to find what was the function before we ended up taking the derivative of it. And that's what the antiderivative is. So anyways, that was a quick introduction to integral calculus, and it's basically kind of like the basis of it. So I hope you enjoyed this video. Like usual, if it's helped you out with anything, please like and comment as to what it's helped you out with. If you're new to the channel, please like, comment, and subscribe. It's greatly appreciated. And yeah, I will catch you guys in another video.